Welcome to Chemical Process Safety. This video is about estimating the damage due to explosions. When an explosion happens, it's very common to relate the known energy of that combustible fuel to the equivalent energy of a massive TNT. You see this all the time in the newspaper or in the news. They say something like, this explosion was equivalent to 5 tons of TNT. And that's helpful because wouldn't know that the normal person knows what a ton of TNT is, but it at least helps you to normalize or to say different fuels have different impacts. So if you relate it to a known amount of TNT, then that helps to compare one versus the other. There's an equation in the book. This is in the back half of chapter 6, where you can do that with the following equation, and then this is going to be helpful for estimating the damage, which we'll talk about in just a second. So the equivalent mass of TNT that explodes is equal to eta, and this is a parameter that's just called the explosion efficiency. Eta is typically between 1% and 10%, so average would be about 5 or 6%, but the worst case scenario would be 10. You multiply eta times mass, which is the mass of the fuel that explodes. I said hydrocarbon because most fuels are hydrocarbons, but it doesn't have to be a hydrocarbon. Delta Hc is the energy of the explosion of the fuel, aka the heat of combustion. And you can find this in the appendix or on the internet. That is a known quantity for every fuel. They have their own individual heat of combustion. And that is all divided by the energy of explosion for TNT. So just thinking about this equation overall, what I'm doing is m times the heat of combustion. That is the energy released by the combustion reaction. ETNT is the energy released by the explosion of TNT. I'm simply normalizing these, and then, of course, multiplying it by the explosion efficiency. Another way to see it is if I multiply ETNT over to the other side, I've got mass times the heat of combustion on both sides. So I'm just, again, relating how much mass of hydrocarbon I have to the amount of TNT. The specific energy for explosion for TNT is given in the book. So there's 3 different values that you can use depending on which units that you like. Once again, I'll just make a note that you should always, in these equations, be mindful of your units. So when you look up the heat of combustion, take note, is that in calories per gram, kilojoules per kilogram, BTUs per pound. Okay, so once I plug everything in, so let's say all I need to know, by the way, is the mass of fuel that explodes. This is lookupable, and then I suppose you need to know this, but you can also estimate that as well. Most times the problem will give it, but if the problem doesn't give it, you're free to make an assumption as long as you state and back that assumption up. Okay, what do we do with this MTNT equation? We're going to, again, use that to estimate the damage that is done. But before we can do that, we also have to define the distance that we're wondering about. So as you might imagine, the closer you get to an explosion, the more damage you would expect. And then as that distance increases, the expected damage is also less. So here they're talking about a scaled overpressure. And that's like the shock wave that results from an explosion. That's the thing that actually does the damage. This is a plot of the scaled overpressure as a function of the distance. So again, as the distance increases, the scaled overpressure decreases. That again makes intuitive sense. So this is figure 623 in your text. And before I talk more about that, we have to know what the scaled distance is. So R is the distance from the explosion in meters. And then MTNT is the mass of TNT, which we calculated from the equation below. So you take the mass of TNT, you take the cube root of it, and you divide that by the distance. That gets you your scaled distance, ZE. So here's a better version of this figure 623 that I was talking about. So again, the procedure is, just to review, you take the mass of fuel that explodes, you convert that to an equivalent mass of TNT. You plug the mass of TNT into this equation for the scaled distance. So you need to know the distance that you're concerned about. Convert that into a scaled distance. Then in figure 623, this is a log-log plot. You find the scaled overpressure. So just quickly to review how these log-log plots work, each line is 1/10 of the way. So if you're looking for 0.4, for example, so 0.1, 0.2, 0.3, 0.4, and then the lines get closer and closer together as you go to the next power of 10. So let's use that example. So 2, 3, 4. If my scaled distance was 0.4, I would follow this line all the way up, and I would find where this intersects. So if I zoom in, it looks to me at least to be a little bit over 100. So a little bit over 100, not quite to 200. So I would call that, I don't know, 105 or so, 110 is the scaled overpressure. And then what do I do with that, you might ask? Well, there's a table in the book. This is table 6.9, where you look up what the overpressure that you have was. I already forgot what my answer was. 100. But what are the units? This is bad plot making procedure. Oh, you know what? I didn't clip the caption. Need to quickly check. Oh, and of course, it's scaled. So scaled means it's the pressure divided by the ambient pressure. So this just means 100 times ambient pressure, so 100 atmospheres. So you take that information and you come over to table 6.9, and we can use whichever pressure scale we like. 1 atmosphere is about 100 kilopascals. So I picked a terrible example because we are in this range of the plot, not necessarily one of the interesting ones. But let's say our pressure had been 9 kilopascals. It really doesn't take a lot of overpressure, by the way, to do a ton of damage, which is somewhat interesting. But you would just basically read off what damage you would expect based on the pressure that you get from the shock wave. Let's look at a quick example. So let's say we've got 1,000 kilograms of methane escaping a storage vessel, mixing with air and exploding. Estimate the expected damage of the blast 50 meters away, assuming that the explosion efficiency is only 2%. So most of this problem is plug and chug, but again, you have to plug and chug into the right order. So I'm going to put in my givens. So the problem says eta is 2%, so 0.2. Mass is 1,000 kilograms. The heat of combustion I look up, I'll talk about this in a second, but this is the lower heat of combustion. And I need to make a quick mention of units here again. So if I look up the heat of combustion and it is in kilojoules per mole, I obviously can't just multiply that by kilograms. So I need to convert this using the molecular weight of methane. And then another thing too is that the heat of combustion by convention is oftentimes negative, but obviously if you have one negative here, you're going to get a negative mass, which doesn't make any sense. So you have to be aware of the differing conventions here. It's just a convention. It's not like I'm magically just making a negative into a positive, but it has to do with energy being given off. In chemical engineering, we oftentimes call that negative, whereas for all combustions and explosions, it's negative. So for whatever reason, ET&T is not negative. It's by convention positive, because I guess most people like to think about positive numbers. But I'm going off on too much of a tangent. And the end punchline is make the conventions equal, basically. I briefly also mentioned that this is the lower heating value for the heat of combustion. So if you look in the appendix, you'll have both the upper heating value and the lower heating value. Remember what that means. You might have covered this in material and energy balances. The difference between these two, the lower and the upper heat of combustion, is the phase of the water vapor that is produced. So in any combustion reaction, you're going to produce carbon dioxide and water. Is that water vapor going to be in the liquid phase or in the vapor phase? For combustions, oftentimes we're going to be forming water vapor. So what this means is that takes energy to vaporize the water, and therefore that's why it's lower. So it's counterintuitive, but trying to think of the best way to explain this. If something explodes, right, it gives off energy. Some of that energy that is given off is going to be consumed by vaporizing water from the liquid state to the vapor state. So that's how I like to think of it. And that's why we should be using the lower heat of combustion for these types of calculations. Anyway, I plug those numbers all in. I get 214 kilograms for the mass of TNT. I then have to find the scaled distance. So I divide 50 by 214 to the 1/3 power. And from that, I get 8.4. So in figure 623, let's go to 8.4. So it's quicker to go from this side. So this is 10, this is 9, 8.4 is going to be right in the middle there. And I'm going to follow this all the way up. And I will find that looks to be somewhere between 0.2 and 0.3. In my solution, I called it 0.25, which is close enough, corresponding to an overpressure of roughly 25 kilopascals, which will demolish frameless steel buildings. So let's check in figure 6.9 and make sure that that is what I've concluded. Yep, we're in this range. Frameless steel panel buildings are indeed demolished. So that is that example problem. And then one more brief mention. Remember, way back in chapter 2, we discussed the probit model, the probability unit model. There was part on that table for explosions. So you could estimate the probability of structural damage that we have from the probit model. So I've done that example calculation, but I won't go through it here in the interest of time. But if you are interested, you can go through and verify that I conclude 78% of structural damage by the probit model. Also, briefly, just to mention, notice that the conclusions that you may draw may be a little bit different. Remember, these models are not end-all, be-all. There's uncertainty, there's caveats, there's all different reasons why you might not get the same answer both ways. So again, this is why it's so important that you always note your methods, note your assumptions, because whenever you make a conclusion like this, you should be able to back it up by saying, using the parameters of probit as defined in the textbook. And then that at least gives you some context to what your conclusion is. All right, that'll wrap up this video. Thanks for watching, and I'll see you next time.